Okay. Yeah. Thank you, Bart. Okay. So I also have an overview, and I know I have to be quite fast. So I try to live up to it and don't make too much delay. So I'm going to talk a bit about the Belgian network. It will be very quick to give you an insight on how our network, railway network, is built up. A bit about Infrabel, the company I work for, because it has changed a lot. We used to be together with the operator, SNCB and MBS. But we've divided, so I want to give you a bit of insight what we do actually, and then I will talk about the challenges we face at Infrabel in applying data science. So let's start. You have to know our network, a railway network, is star-shaped towards Brussels in the middle. And on average, on a weekday, we get 3,800 passenger trains. We have 770 freight trains, and the numbers we get from SNCB in 2012 were that there were on average some 760,000 passengers, and 57% of the passengers that sees Brussels per day. So what is Infrabel? Actually, we have a CEO who manages 3 directorates, asset management, traffic management and services, and build. And the part I'm belonging to is the middle one, the traffic management and services. So what do we do? All these 3 directorates. The asset management part is mainly for maintenance and renewal of the rail infrastructure. So all the tracks, the catenary, the signals, the level crossings, they maintain and renew. On the other hand, build director, they have the major investment projects from the rail infrastructure. So if you know the Schumann-Josephat tunnel and the track to the Brussels National Airport from Mechelen, well, that's those kind of projects which they manage. And then the big part in traffic management and services, we have the train path assignment to the operators. We also do the planning. The daily traffic operations are also situated in that department, and all the support services, like for instance controls and audits, safety regulations, and of course business analytics, which is a very small part in it. So we have 5 priorities at Infrabel. Safety comes first. We like to get the trains on time, and we provide a network for all trains today and tomorrow, so we have to have enough capacity. We tend to be a financial healthy company, and we are also trying to be on one line with society. So coming back to the main point, the data science at Infrabel. Well, actually, I have to say we are going a step-by-step approach, because Infrabel is not used to having large statistical models and analysis done. So the main part that they are using now from statistics is the pie charts, bar charts, tables. And statistical analysis is something we are trying to get into the company. So there's lots of backward looking at the data. Historical data are explored in a way with pie charts, bar charts, but we like to go to the predictive modeling and looking forward. Now, a big part of the data science, as you all know, Sven told it, there's a large part you have to get your hands dirty with the data and clean them. But in our company, it's also a big issue that we have to get a master data management. So it's step by step that we are trying to get it established in our company. And since there is also, I don't know if many of you are coming from a company, but there's always a large fight going on between business and IT. So that's also the case at Infrabel. And actually, I find myself sometimes a bit as how to say, an intermediator between business and IT. So the other thing we are facing with is that there's a lot of silo thinking, not only silo data, but also everybody is inside their little department and they don't know how to share the data with others and what's the use of sharing, because it's their data. So we have to also step by step trying to get the people thinking more transversal and thinking about integrated data. So we would really like to turn data into information, and especially also we need to translate the business needs into answers. So to prove that the data science, the statistical analysis and modeling really is an support for them. So some of the challenges we face is, I talked about turning statistics into statistical analysis. And these are a few examples I have. And one of them is that the business, they explore the data on a daily basis, based on what they know from experience, based on what they see, what they hear coming from the people at the terrain. They like to dig in the data and really look at, for example, detailed information about the train delays. So one of them came up with the fact that trains of a certain type, if they have a change of crew, the train conductor has to change at a certain point, then this kind of train type has more delay in the Brussels South station than all the other train types who are also having a train conductor change. So that was a fact, and we tried to make that into a hypothesis to test. So we thought about, okay, let's test, see if this is a systematic problem. So if this train type with the planned crew switch around 3 or 4 minutes, do they have more average extra delay in the stops than any other material with the planned crew switch between 3 and 4 minutes time? We looked at a larger period, we also looked at the weekdays, and we looked at the whole network, because we were thinking if it is a systematic problem. Yeah. Is it okay? No. So we thought if this... Okay. Is this isn't getting any better? Yeah? Okay. So we were thinking if it is a problem on the whole network, then we have something we could take a look into, and we can get an action from that, and maybe talk about another kind of crew switch or changing the train types, etc., etc. Now, when we looked at it, then it seemed that this train type we were looking at had the largest average delay in Brussels South, with a planned crew switch around 3 minutes. But there was another train type that had the largest average delay in Hasselt, so not in Brussels South. And it was when we looked at the 4 minutes planned crew switch. So it seemed that our hypothesis was location dependent. And maybe the personnel switch was not the only reason for the delay. So we thought, okay, we tried the hypothesis again, but only for the Brussels South region. Now, there was another thing when we were discussing this with people who explored the data. Then yeah, we drew some box plots. That's also one thing we would like to improve on. That's instead of using the bar charts and the pie charts and talking about averages, that people are also looking at the spread of the data, at least the spread, please. So, and a box plot is something we like to throw in, and it's almost getting there. It's not everybody's favorite graph, but if they see us coming, but there are people who tend to enjoy these graphics. Now, the problem was that after discussing it with our colleague, that it seemed that the delays he was looking at, where he thought, okay, my train type, my train material, I'm seeing as the worst. Well, that was actually, he was looking at the outliers in the data. So our conclusion was, okay, the data in the exploration phase was actually a subset of the whole data package we looked at. So the outliers in our data were less than 25%, and my question was, or the business question was actually find the systematic problems in the outliers. But my question then is, okay, but is this subset still large enough to perform hypothesis testing? I don't know if any one of you has the same problem. And also my idea is how to prove a business's gut feel if it is about outliers in the data. And that's a big problem for me, being trained as a robust statistician into the data, into the problems of outliers. So I'm really looking forward to have a discussion on that one. So another thing is about enriching the data. This was the goal in the project, was to find a pattern in the signals that were past at danger events. And the problem there was, okay, we had to find a pattern, but there was no information about the non-events, or not the same information at least. There were many qualitative variables, around 50 variables we had in the data set, but it's rather a small sample size we're talking about, luckily, because otherwise we would have more problems. There are 100 signals passed at dangers. That means that the driver drives to a red signal. So how can we find a pattern if we only have 100 events per year? And what will come out of it? So we tried different techniques just to find in those 50 variables, first reducing them, what are the most important variables to use in a further analysis. Then we tried the clustering. Can we find some interesting patterns in that? And we also tried a logistic regression to see, can we find the probability of such a signal passed at danger. Now, this is typically also history of the garbage in, garbage out, we all know, because the 50 qualitative variables, of course, they were gathered by the people. They were coming from questionnaires when taking from the train conductor when a signal was passed, and then they were transferred to an Excel file, and they had data for over 5 to 6 years and even more. But the problem was that the data, the information they gathered from the people changed over the years. So we didn't have consistency in the data to get something out of it. So we had a promising output in the logistic regression we did, so to predict the probability of such a signal passed, but we still had a model error of around 35% of misclassifications, and the data we used came actually from another database. They didn't came from their data. So there was also, it was no answer to the initial business question. So there we were faced with the problem, if there's no relevant information in the data, there will be no relevant analysis done. So and then another thing we tried is to get new insights by using innovative models, which means we used, together with the University of Antwerp, we tried in 2011 a frequent pattern mining. The idea was, let's try to discover the trends or patterns of the delays, such that the business will be pointed out where to look first for the problems and get into detail at certain locations. So we had to translate the problem into the algorithm context first, and I'm not going into the technical detail, but the thing was that there were moving time windows, which we took about around 30 minutes of delayed trains. So we looked inside the windows and tried to establish which trains were together in that 30 minutes frame, and looked who was there at the same time, and the number of days that the train was delayed was actually our output. We looked at the single events, the trains themselves, and we had an example of a series of 4 trains which had a delay of more than 3 minutes on 15 of the 31 days we looked at, because it was a small sample we took to test if this algorithm could really help us. And if we looked at a larger pattern, that would be the train 8904. If it had a delay, then the train 8905 and 8963 also had a delay. And this occurred, a delay of more than 3 minutes on minimal 7 days, and a delay of more than 6 minutes of minimal 4 days. So that kind of patterns we were actually looking for, but the problem with the data was that to find these patterns, there was no automatic rule that could point us to these interesting patterns. And so the data had to be manually checked for, pattern by pattern, to see if it was interesting enough. So a colleague did this, and he found this particular pattern. And actually what was going on is that you see on the right-hand side, you see a planning. And what happened was that the 8904 train, he came in from the left, and the yellow one is the 8963 train, comes in from the right. Okay, everything, the red train leaves for the direction Kortrijk. The yellow one stays a bit on the platform. Then the purple one is the 9805. He drives into the station from Brussels. The green one is the one coming from Ghent. And then if we move further in time, the purple one leaves for Kortrijk, the yellow one leaves for Ghent, and the green one leaves for Gerardsbergen. But the problem was, if the red one is too late, then all the others who have to pass the same infrastructure also would be too late. So it's actually an insight for the people on the terrain that if they change the order when the red train is delayed, and if they change the order they drive out again, then there could be an avoidance of an accumulating delay. So these were the kind of pattern we were really interested in, but the problem at that time, in 2011, was that we didn't have an automated rule that could point us to these interesting patterns. And if this is data coming from 31 days and giving out hundreds of patterns like these, we're not going to manually search them. So at that time it was stopped, the project, and we didn't go further into detail. This was another kind of visualization we used. We also, besides the box plots, this is actually, you could say, this is a percentile plot, so you can see the box plot in there. And maybe this one was a bit more open for our business. And the thing is, the train causing the trouble, if you look at the horizontal dotted green line, that's the line of the 6 minutes delay. All above 6 minutes will be looked at and will be taken into account into the punctuality numbers. So 50% of the time he had more than 6 minutes delay. So it really was a problem to look into and maybe to check out if the local operators could try to change the scheme, the schedule. Now, because we don't want to wait too long, then we tried, that is more recent research, together with the University of Hasselt, and Gert, the student, as a master thesis student, he looked into this, and we were testing out if the process mining could help us to discover trends and patterns in conflicts. So to translate the problem again into the algorithm context, a train conflict was defined as the aberration between a planned train path and a real train path. So what was done? We compared the consecutive signals on the train path, and then there were measures proposed to calculate for the conflict sensitivity. And it was the deviation degree, how much the train paths differ from each other, and then also a deviation in diversity. So the length and the depth of the deviation was taken into account. Now, if we were going to search for the significant deviations degrees, there was a Kruskal-Wallis test proposed. And then, of course, if we know which of the deviations are significant, statistically significant, then we can look into, is this deviation structural or sporadic? Where is it in time? Which trains are involved on which days? And then the types of deviation, to look into that, there was a clustering proposed on these deviation degrees. So what came out of it, and this was for us more interesting, because now we had an automated rule which could point us out which of the connections, there are anonymized here, which of the connections are really worthwhile or to look into detail. So in this case, the numbers 2, 3, and 8 are connections which would be interesting because the sensitivity to the deviation in their train paths is really statistically significant from all the other connections in that area, because we looked at the station area of Leuven there. So we can go into detail for these numbers 2, 3, and 8. Also, that was based on the deviation degree, but there were also the length and the depth of the deviation included. There were measures for, and if we put them all into a scatter plot, you could also look into which ones are situated in the upper right corner and look into those connections, because there are the ones that are really having deviations which could be interesting. So the numbers 2, 3, and 8 were marked here. 3 has not that much deviation in the length or the depth, considering the numbers 2 and 8, but maybe this could point out that although there is a deviation, a certain degree of deviation, that maybe it's always the same kind of deviation we look into. So that would be interesting to check out if these routes that were taken, they were probably for one and the same conflict. Then the clustering that was done on these deviation degrees, those were for a certain connection. And these clusters could show different behavior during time, for instance. And the thing is that it should be checked out with the traffic operators why they are choosing a train path at that certain point of time. Maybe it's because there are works going on, maybe it's because there are problems with crossing trains like the ones you saw in the previous example. So it really is interesting that we now have an algorithm that points us in the right direction, but of course the results still have to be checked with the people from the terrain. And I think I would like to conclude in saying we have many interesting cases, but the results of the more sophisticated and advanced statistical modeling and analysis, they need to be fine-tuned for practical use. So it's interesting to test these things out, but it really has to be a practical use for people on the terrain or people that are really involved in preparing actions for management or for planners to have feedback and tell them, could you maybe plan the trains in the another way around, because it would be better and because we would find less delay. There are also open questions from my side on the small sample statistics, and how can we take representative samples from big data? I think it's something that is puzzling me very recently. And one thing we have to overcome still is the hesitation from the business to adopt these statistical results, because they're not used to this kind of models and to this kind of results, because they are really into the statistics, like the pie charts and bar charts. It's really not simple to let them understand what it means, this result or this prediction. Or so anyone who has some ideas on that, I will be happy to talk about it. So for me, data science at Infrabel is a bit of change management. Thank you for listening, and if there are any questions.
Yes, I think you're not the only one I was thinking about. Silo thinking was something that I noticed in banks and in other companies, so don't worry about it. It's typical for you. People who are having questions or perhaps answers to
well, actually, I arrived a bit late, so sorry if anyway. So you have problems with the low statistics on your samples. Why exactly do you take a sample then?
No, it's not only from the small samples that we take, a subsample. So those are two different questions. My first question is on what do I do when I have small samples and I want to have some statistics on that. And the other one is if I'm having big data, you don't develop your model on the whole big chunk of data immediately. You have to test it out. And the question there is, what is a representative sample of that? And not only from the big data, but for instance, if I take these 100 signals past a danger a year, when will I have representativity of the data for the problem that emerges there? How many years do I have to take into account before I can have a valid model?
My answer to that is you just don't go that far. In fact, I work in a bank, we do risk analysis there too. We have also very small samples, luckily, because there are not too many defaults, so people who don't pay back their mortgages, for example. And you just don't go that far in the statistical testing with the p-values and everything. You just try to predict whatever you have and whatever you see in the data. And yes, sometimes it's less accurate, 35% in the specification. Yeah. Sometimes we also make models with ROC curves where you have 60% or less any out of the curve. That's the only information that we have, so you go on to the approach.
But the problem there I have is that if you're going to present these results to management or to people who are not that familiar with the statistic, then how can they be convinced that it is a good model, that it is still a good model?
Still better than a pie chart.
That's true.
Could you use all the data you have when you don't have a signal or a danger? Because it's an unbalanced problem. You have a lot of data and it's safe, so maybe there is an idea there. It's not only the problem, but only when there is no, but also when there is no problem. Maybe to detect features.
That would be an interesting idea.
Yeah, oversampling and all the classical tricks to balance your data more than you can't do magic at it. So it always has to rely on these kind of tips and tricks to get more balance in the data. Familiar problem.
I have a different question. Do you try to actively gather more data?
In a certain way, yes. When we are going to look over the wall to our colleagues at the infrastructure department, so they have lots and lots of data coming really from the terrain directly. But the problem then is that if we want to make a link between the data we have from the train routes driving every day and link them with the infrastructure messages, there's sometimes a gap because the primary key is missing. So the train number we have is not the train number they have, or it's maybe the train number is missing. So there's a lot of cleaning up and a lot of thinking about how we can merge those two data sets together.
We are not laughing with you, we are
No.
laughing because we recognize the problem.
Do you have computing power available at your service?
I have to talk to IT. But there is computing power, yes, but I'm not sure how big we're
So you cannot use all the big data anticipating yourself.
No, we can use, but the question is, do we have to use them all? Sometimes maybe it's better to take a sample and to train the model and then validate it afterwards. But
Even that you don't use that.
The English railway, they're publishing real-time many of their data about trains. Do you have something similar?
not that I know, or not yet, I should maybe say. But that's not my decision to take.
Do you have their plans to do something?
No, I'm sorry. I could ask.
Would be a nice one.
And do you know what your colleagues in the other countries are doing on that level? Do they face the same problems?
Well, we talk to them from time to time, but on this particular modeling, we haven't had a discussion yet. But it's planned for 2016 to get together again. Yeah. But for example, the percentile plots you saw, that's an idea actually of the Dutch railways.
Hey, I hope you liked this presentation. This presentation was held in the Brussels Data Science Community Meetup. If you want to know more of when these meetups are taking place, just check the link below. Bye-bye.